Hi, welcome back. In this lecture, I would like to talk about definition of a process. So I will describe more fundamentally what constitutes a process in operating system context. You probably remember that I already used the word process, especially process and programs. In this lecture, I will describe more formally what constitutes a process. So first, let's give a definition of a process. So a process is an instance of a program running. So you see already there is a strong relation between program and process. However, they are not the same thing. So a program is a passive entity that is stored on a disk or in a, and this passive entity is actually the executable file. On the other hand, the process is an active entity. The program becomes a process when an executable file is loaded into the memory and so therefore can be executed. An important aspect when it comes to program and processes is the fact that one program can have several processes. So for instance, we have a program. We start with one process. At a certain point, we want to distribute the task across different processes, so we can actually spawn different processes. And at this point, our program can contain different processes. So for instance, when you're running a supercomputer, you will spawn many different processes that will be mapped to different computing nodes of the supercomputer. But we will have one program that is actually spawning and using several processes. So look at more what constitutes a process. Well, a process is actually much more than a program code. There are different parts that constitute a process. So here in this plot, you see the different parts that are constituting the process. So at the bottom, we have a so-called text section that includes all the executable code. We have a data section that contains all the global variables. Then we have a part of the memory that is divided in heap section and the stack section. So the heap section is the memory that is dynamically allocated during the program runtime. So for instance, if we have a C code, all the memory that is allocated through malloc will go to the heap section. On the other hand, all the temporary data storage, when for instance invoking function parameter, return addresses, and local variables, they will live all on the stack. So just to summarize, there are different parts that constitute a process: text section with the code, data section with a global variable, and then heap section for dynamically allocated variables, and the stack section for temporary data storage, like function parameters, return addresses, and local variables. So here, again, a C code, and we see how different parts fit to different parts of the process. So for instance, here we have dynamically allocated that will go to the heap. An important building block of a process is so-called process control block, or PCB in short, that store all the information of each process. So each process will have a PCB. Here on the plot, we have the different part of the PCB. So for instance, we will have the process state, a process number, a program counter, a number of the register, memory limits, and the list of open files for that particular process. What is the fundamental process data structure in the Linux kernel for the process? Well, so this is represented by the task that is a C structure in the Linux kernel, and you can find it in this include file, the definition. All the active processes in Linux are represented using a doubly linked list of task structure, as you see here on this diagram. So we have link in one direction, but also in this direction here too. And this constitutes a double linked list data structure. So each process is identified by identification, process ID, that is a unique identifier called the PID. So this is the process ID. The kernel allocates PIDs to processes in a strictly linear fashion, so it just increases in a linear fashion. There are also a number of system calls to get retrieve the ID of the process. For instance, get PID, that is a system call that will return the PID of the invoking process. So the processes can be in a different state, new when the process is being created, ready when the process is waiting to be assigned to a computing unit, to a processor, running when the actual instruction of the process are actually executed. We might have a process in the waiting state when the process waits for an event to occur. And last but not least, we might have a process that is in terminate state. The process still has to finish the execution time. So this is the last slides of my lecture. Talk to you soon.